Good morning. Take a seat. Find a comfortable spot. I see some of you are still waking up. I see a few coffees out there on the desks. That's good. Actually, that is perfect. Don't drink it yet. Just look at it. Watch the steam rising up. That little cup of coffee is going to be the most important thing we talk about today. It is going to tell us everything we need to know about the universe, about how it began, and more importantly, how it is going to end. Now, does that sound like a big claim? Maybe, but physics is made of big claims built out of little observations. We look at the little things, a falling apple, a swinging pendulum, a cooling cup of coffee, and we try to find the rules that play the game. The rules are the same everywhere. That is the miracle. The same rules that govern the steam curling off your cup govern the swirling of galaxies a billion light years away. So let's look at that coffee. It's hot, right? At least, I hope it is. If you leave it sitting there on the desk while I ramble on for an hour, and I probably will ramble, what happens to it? You know the answer? It gets cold, it cools down, the heat leaves the coffee and goes into the air of this room. Eventually the coffee is the same temperature as the room. We call that thermal equilibrium, but that's just a fancy way of saying everything is evened out. Now here is the question that keeps physicists awake at night. Have you ever seen the reverse happen? Have you ever sat in a room staring at a cup of lukewarm day-old coffee and suddenly seen it start to boil all by itself? Have you ever seen the heat from the surrounding air suddenly rush into the cup, making the room a little colder and the coffee a little hotter? No, you haven't. Nobody has. If you saw that happen, you'd run out of the room screaming that you'd seen a ghost. It just doesn't happen. But why? This is where it gets interesting. If you look at the fundamental laws of physics, the laws we spend years teaching you in these classrooms, there is nothing in them that forbids it. If I write down Newton's laws of motion, or the laws of electricity and magnetism, they work both ways in time. If I took a movie of two billiard balls colliding and played it backward, it would look perfectly normal. Physics doesn't care about forward or backward when it comes to two atoms hitting each other, so if the laws of the tiny parts work both ways, why does the big picture only go one way? Why does the coffee always cool down and never heat up? Why does an egg break but never unbreak? Why do we remember the past but not the future? This one-way street is what we call the arrow of time, and to understand it, and to understand the ultimate fate that awaits everything, we have to stop looking at the coffee as a brown liquid and start looking at it for what it really is, a pile of jiggling atoms. You see, that's all heat is. We use these words heat, temperature, thermal energy, but nature doesn't know those words. Nature just knows motion. If you could shrink yourself down until you were smaller than a dust mote, and you jumped into that coffee cup, you would see a chaotic storm. The water molecules are banging into each other, spinning, vibrating, rushing around at tremendous speeds. That is what hot means. It just means fast jiggling. The air molecules in this room are doing the same thing, but they are jiggling a little slower. That is what cold means. Now think about what happens at the surface where the coffee meets the air. You have the fast jiggling water molecules banging into the slow jiggling air molecules. What happens when a fast ping-pong ball hits a slow ping-pong ball? The fast one slows down and the slow one speeds up. They share the energy. The heat moves from the hot coffee to the cold air. But wait, occasionally, just by pure luck, a slow air molecule might hit a water molecule in just the right way to give it a kick and make it go faster. It happens all the time. But it is overwhelmingly more likely that the fast ones will lose speed to the slow ones. This brings us to a concept that scares a lot of students, but it shouldn't. It's the idea of summing things up. In mathematics, we call it integration calculus. But forget the symbols for a moment. Think about the idea. We can't track every single atom. There are trillions of them in a single drop. It's too complicated. If we had the biggest computer in the world, and let me tell you, the ones we have now take up entire rooms and they still couldn't do it. We couldn't track every collision. So we don't try. We cheat. We use statistics. We say, I don't care what atom number 5002 is doing. I want to know what the crowd is doing. When we look at the crowd, we see the truth. There are simply more ways to be disordered than there are to be ordered. Let me give you an analogy. I like analogies because the math is just a translation of common sense anyway. Imagine you have a deck of cards. You buy it brand new from the store. You open the box. The cards are in perfect order. Ace, king, queen, jack, all the way down suit by suit. That is a state of high order. We call this low entropy. Now throw the cards in the air. Let them flutter down to the floor. Pick them up. Are they in order? Probably not. Shuffle them. Are they in order now? No. Why? Is there a physical law that says the cards cannot fall into perfect order? No. It is physically possible that you could throw the deck in the air, and they would land perfectly arranged by suit and number. It could happen, but will it? No, because there is only one way to be perfectly ordered, and there are billions and billions and billions of ways to be mixed up. The odds are so stacked against you that you could shuffle that deck every second for the age of the universe and never see them come back to the original order. This is the second law of thermodynamics. It is the supreme law of the universe. It says that things tend to move from order to disorder, from unlikely states to likely states, from special arrangements to boring average arrangements. The hot coffee is ordered in a special way. All the fast atoms are separated from the slow atom. Fast ones in the cup, slow ones in the room. That is a special separated arrangement. It's like having all the red cards in one pile and all the black cards in another. As time passes, they mix. The fast and slow mix together until everything is lukewarm. That is the mixed up state. The disordered state, high entropy. Once they are mixed, you can't unmix them for free. You can't just snap your fingers and tell the fast atoms to go back into the cup. The probability is effectively zero. This is why the universe has a direction. We are sliding down a slope of probability. We are moving from a state of order to a state of disorder, simply because there are so many more ways to be messy. Now you might ask, so what? Who cares if my coffee gets cold? I'll just reheat it. And you can. You can put it on a hot plate. But think about what you are doing. To heat the coffee back up, you have to burn coal or gas at a power plant or use a chemical reaction. You have to create more disorder somewhere else in the universe to create a little bit of order in your cup. You are paying a tax. You can never break even. The total amount of messiness in the universe always goes up. This concept, this flow from hot to cold, from order to disorder, is the only reason anything happens. Anything at all. Think about the steam engines that started the Industrial Revolution. How do they work? You have a really hot fire and you have cold water or air. The heat wants to flow from the hot side to the cold side. We put a piston in the middle and we say, okay, if you want to go over there, you have to push this wheel for me first. We steal a little bit of work from the flow. It's like a water mill. You have water up high, that's the heat, and a river down low, that's the cold. The water wants to fall. We put a wheel in the way, and the falling water turns the wheel. That's an engine. That's life. That's us. You, sitting there, you are a heat engine. You are taking ordered energy in the form of food chemical structures that are put together in a very specific low entropy way, and you are breaking them down. You are burning them. You are keeping your body temperature at 98 degrees while the room is 7. You are constantly shedding heat, shedding disorder into the room. You are increasing the entropy of the universe just by breathing. But here is the catch. Here is the part that starts to get us toward that terrifying conclusion, I promise. The water mill only turns as long as there is a difference in height. If the water at the bottom gets so deep that it rises up to the level of the top, the flow stops, the wheel stops turning. The steam engine only runs as long as the fire is hot and the outside is cold. If the fire goes out or if the outside gets as hot as the fire, the engine stops. Work, useful, interesting activity, can only happen when there is a difference, when there is a contrast. Hot versus cold, high versus low, order versus disorder. We are living off of those differences. We are spending the inheritance of the universe. Every time a star shines, it is taking a concentrated pocket of hydrogen gas, very ordered, and fusing it into helium, spraying out heat and light into the cold darkness. It is mixing the hot and the cold. It is raising the temperature of the empty space a tiny, tiny bit, and lowering its own temperature. It is smoothing things out. Nature hates gradients. Nature hates differences. It wants to smooth everything out. It wants to spread the butter evenly over the toast until you can't tell where the lump was. We can describe this mathematically with what we call a gradient, a slope. Physics is all about things rolling down slopes. A ball rolls down a hill. Heat rolls down a temperature gradient. Electricity rolls down a voltage gradient. And just like the ball stops when it hits the flat bottom of the valley, the physical processes of the universe stop when the gradients disappear. When the coffee reaches room temperature, the flow of heat stops. The micro events, the atoms hitting each other, continue. They are still jiggling, but the net flow is zero. Nothing useful is happening anymore. You can't run an engine off a cup of lukewarm coffee in a lukewarm room. There is no potential. There is no dry. Now I want you to perform a mental leap with me. We have been talking about cups of coffee and steam engines, but the laws of physics are universal. They don't change just because things get bigger. Imagine the universe, the whole thing, all the galaxies, all the stars, all the vast clouds of gas, all the dark empty spaces. When we look out at the night sky, what do we see? We see bright spots and dark spots. We see the sun, very hot. We see the deep space between the stars, very cold. That is a massive temperature difference. That is a massive battery that hasn't run down yet. The universe is full of these gradients. It is full of unevenness, and because it is uneven, things happen. Stars are born, planets form, life evolves. We have lectures about physics. It's all happening because the energy is flowing from the hot spots to the cold spots. But if the second law of thermodynamics is true, and believe me, it is the one law I would bet my life on. If your theory disagrees with Maxwell, so much the worse for Maxwell. But if it disagrees with the second law, you are hopeless. Then this flow cannot last forever. The universe is a closed system. Now some folks might argue about the edges, but for all intents and purposes, there is nowhere else for the heat to go. We are in a giant box, and inside this box the coffee is cooling, the stars are burning through their fuel. They are dumping their heat into the cold vacuum. Slowly, inexorably, the cold vacuum is getting a tiny bit warmer, and the stars are getting colder. The gradients are flattening out. The water is rising in the bottom of the pool. This leads us to think about the beginning. If the universe is winding down, getting messier and messier every day, that implies something profound about the past. It means that yesterday, the universe was more ordered than today, and a year ago it was even more ordered. If you wind the film backward, you come to a point, the Big Bang, where the universe must have been in a state of incredibly, unbelievably low entropy. It must have been wound up tight, like a clock spring coiled as tight as it could go. We don't know exactly why it started that way. That's a question for the philosophers, or maybe the theologians. As physicists, we just look at the evidence, and the evidence says the clock was wound, and ever since that first moment, it has been ticking down. We are living in the ticking. That's what time is. Time is just the measure of things getting messier. If nothing ever changed, if nothing ever got messier, there would be no way to distinguish the past from the future. The arrow of time is just the arrow of increasing entropy. So we have established the rules of the game. Rule 1, energy is conserved. You can't create it or destroy it. You have what you have. Rule 2, entropy increases. The quality of that energy gets worse. It spreads out. It becomes useless heat. Now I want to talk a little bit about what useful means, because this is where the math of energy gets tricky for people. We talk about conserving energy, right? Turn off the lights to conserve energy, but I just told you energy is never destroyed. So why do we care if we leave the lights on? The energy doesn't vanish. What we consume is not energy, it is available energy. We consume order. When you turn on a light bulb, you are taking electricity, which is a highly ordered flow of electrons, all marching in step, and you are turning it into light and heat. The light bounces around the room, gets absorbed by the walls, and turns into low-grade warmth. The energy is still there, the room is a tiny bit warmer, but you can't take that warmth and turn it back into electricity to run the light bulb. You have degraded the energy. You have taken a high-quality resource and turned it into low-quality waste. This is what we call free energy. Not free like a free lunch, but free as in available to do work. In thermodynamics, we have an equation for this. We say that the change in free energy is equal to the change in total energy minus the temperature times the change in entropy. I won't write the symbols on the board because symbols can be scary, but listen to what the sentence says. It says that the amount of useful energy we have depends on how much entropy, how much disorder we create. The more disorder we make, the less energy is available for the future. Every process in the universe is gnawing away at the free energy. We are eating the order. In the 19th century they worried about running out of coal. Then we found oil. Now we worry about uranium. But those are just details. The real fuel is the low entropy state of the early universe, and we are burning it just by existing. So we have a universe that is expanding, cooling and mixing. We have a one-way trip from a tidy beginning to a messy future. Now let's pause for a moment and think about the scale of this. When we talk about these things in physics, we often use idealized examples. We talk about a perfect gas or an isolated system, but the real world is messy. The real world has friction. Friction is the enemy of order. Rub your hands together, go on, do it, feel them get warm. That's mechanical energy, the ordered motion of your muscles turning into heat. Friction is everywhere.
There is friction in the tides of the ocean, rubbing against the floor of the sea. There is friction in the plasma of the sun. There is friction in the rotation of the galaxy. Friction is the mechanism of the second law. It is the agent of chaos. It ensures that you can never get 100% efficiency. You always lose a little bit. You always pay the tax. This means the process is relentless. There is no way to stop it. You can build a refrigerator to cool down a small space, to locally reverse entropy, but you have to put a motor on the back that heats up the kitchen more than you cool down the inside of the box. You can't win. You can't even break even. So where does this lead? If we project this forward, not just to tomorrow or next year or even the next million years, but if we use the calculus of limits, if we ask, what happens as time goes to infinity? What happens when the limit is reached? Calculus is the study of where things are going. If you have a curve that is going down, 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 you want to know, does it hit zero, does it level off, or does it go on forever? In the case of the universe, the curve of useful energy is going down, the curve of entropy is going up, and because the universe seems to be a finite package of energy in an expanding volume, these curves have a destination. They are heading toward a state where everything is the same. No more hot stars, no more cold space, no more planets, no more light, just a vast uniform bath of useless radiation. This is the concept I want to plant in your heads for the second half of this discussion. We call it the heat death. It's a terrible name, really, because it sounds like we're all going to burn up. It's actually a death by heat, specifically the death of heat flow. It's a death by ice. It is the big freeze. But before we get to the freezing dark, we have to understand the journey. We have to look at how the stars are fighting this battle right now. Look at the sun. It seems so permanent, doesn't it? The ancients thought it was a god, perfect, eternal, unchanging. But we know better. We know it is a machine. And like any machine, it has a fuel tank. And like any fuel tank, it has a gauge. And if you know the physics, you can read the gauge. We can calculate the rate. That's another calculus word. Rate. How fast is the hydrogen turning into helium? We can measure the neutrinos coming out of the sun, little ghost particles that tell us what's happening in the core right this second. And we can tally up the legend. The sun is burning 600 million tons of hydrogen every second. Every time I snap my fingers, snap, 600 million tons gone, converted into energy and ash. The ash is helium. The energy is sunlight. That sounds like a catastrophe, but the sun is very big. It has a lot of fuel. It can keep this up for another 5 billion years. But 5 billion is a number. It is not infinity. It is a finite number. And there are stars out there much bigger than the sun. The big blue giants. They burn their fuel furiously. They live fast and die young. They burn through their tank in a few million years. And then bang, they explode. Supernovae. They scatter their guts all over the galaxy. Then you have the little red dwarfs. They are the misers. They sip their fuel. They will burn for trillions of years. But eventually, even the misers run out. So imagine this timeline. We are currently in what we might call the era of light. The party is in full swing. The chandeliers are blazing. The band is playing. The champagne is flowing. But we are looking at the clock on the wall, and we are looking at the supply of champagne bottles in the cellar. We can count them, and we know that no new bottles are being delivered. The truck isn't coming. The universe started with a fixed inventory of order. We are consuming. In the next part of this talk, I want to take you on a trip into that deep future. I want to use the tools we've just discussed, entropy, probability, the arrow of time, to predict exactly what happens when the bottles run dry. We are going to watch the stars go out one by one. We are going to watch the galaxies dissolve. We are going to talk about black holes, those mysterious drains in the fabric of space-time, and we are going to see that even they are not immortal. It is a strange thing to think about. We spend our lives trying to build things, to create order, to make something lasting. We build pyramids, we write books, we discover laws of physics. We are fighting the slide. We are trying to push the rock up the hill. But the hill is made of ice, and gravity is patient. The physics we have discussed today, the simple cooling of a coffee cup, tells us that the rock eventually comes down. The coffee eventually gets cold. The universe eventually forgets we were ever here. That sounds grim, I know. But there is a beauty in it too, a terrifying, austere beauty. It means that this moment right now, this era where stars shine and people think is incredibly precious, it is rare. It is the brief flash of a firefly in a long dark night. So keep your eye on that coffee cup. It's not just a drink, it's a microcosm of the cosmos. It is demonstrating the most ruthless law in nature. It is showing you the future. When we come back, we are going to follow that future to its absolute limit. We are going to see what happens when the universe reaches the ultimate state of equilibrium. When the jiggling stops, when the time itself loses its meaning. We are going to talk about the end. But for now, drink your coffee before it gets cold. Welcome back. I hope that coffee was good, even if it was lukewarm. In the first part of this discussion, we looked at the small picture. We looked at a cup of coffee cooling down in a room. We saw that nature has a preferred direction. It likes to mix things up. It likes to take the hot and the cold and mash them together until everything is a boring gray average. We called this entropy. We established that you can't get something for nothing. Every time you do anything interesting, run an engine, think a thought, or scramble an egg, you are paying a price. You are creating disorder. Now I want to take that simple idea and blow it up. I want to look at the biggest machine there is, the universe itself. You see, for a long time people thought the universe was static. They thought it was just there, eternal, unchanging, like a stage that was always set. But we know now that isn't true. The universe is changing, it is evolving, and if it is evolving, that means it is going somewhere. Think of the universe like a giant mechanical clock, a really beautiful, intricate grandfather clock. When we look at it today, the pendulum is swinging, the gears are turning, the hands are moving, it's full of activity. But why does a clock run? It runs because someone at some point wound it up. Someone put energy into the spring. They created a state of high tension, high order, and now the clock is slowly spending that energy to keep moving. The winding up was the Big Bang. We don't know exactly how the winding happened. That's a mystery that keeps us humble, but we know it must have happened. At the very beginning, the matter in the universe was incredibly smooth, incredibly hot, and arranged in a very specific way. It was a state of incredibly low entropy. It was a full tank of gas, and ever since then, for about 13 or 14 billion years, the universe has been driving down the highway, burning that gas. Right now, we are living in a very flashy era. Astronomers call it the Stelliferous Era. The era of it's like the fireworks display at the beginning of a party. We look up and see billions of suns, but what are they doing? They are taking the simple ordered hydrogen left over from the beginning, and they are crushing it. They are fusing it into heavier elements, helium, carbon, oxygen. In the process, they are blasting energy out into the cold void. They are trying to heat up the universe, but the universe is very big, and it is very cold. The average temperature of empty space is about 3 degrees above absolute zero. That is cold. The stars are hot spots in a cold room, and just like your coffee cup, the heat is rushing out. Now we can use our way of thinking, our calculus of rates and changes, to figure out how long this party can last. It seems like it will last forever, doesn't it? The sun has been there every day of your life. It was there for the dinosaurs. It will be there for your grandchildren. But a long time is not forever. We can calculate the burn rate. We know how much hydrogen is in a galaxy. We know how fast the stars turn it into ash. And if you do the division, you get a number. It's a big number, but it's finite. Eventually the gas runs out. It won't happen next Tuesday, but in a few trillion years, which is just a blink of an eye in the life of the cosmos, the last new star will be born. It will sputter into life, burn its fuel, and then, that's it. No more gas. The tank is empty. So what happens then? The universe doesn't just stop, it enters a new phase. We call it the degenerate era. It's a terrible name, I know. It sounds like the universe is hanging out in pool halls and getting into trouble. But in physics, degenerate just means matter that has been crushed down into a very dense state. When the stars die, they leave behind corpses. The little ones become white dwarfs, hot balls of carbon, cooling slowly like embers in a campfire. The big ones become neutron stars or black holes. So imagine the night sky in this future. The bright, beautiful stars are gone. The spiral arms of the galaxies have faded. All you have are these dim, cooling embers, drifting in the dark. If you were living then, and you'd have a hard time of it, because it would be very cold and very dark. You would see the white dwarfs slowly fading from white to yellow to red. They are radiating their stored heat away. They are trying to reach equilibrium with the cold space around, and eventually they will go out. They will become black dwarfs, just cold lumps of matter, floating in the void, invisible. The universe will be a graveyard of dead stars. But wait, We aren't done yet. Nature is very persistent at cleaning up. We still have the black hole. Now back in the day, we used to think black holes were like the roach motels of the universe. Things check in but they don't check out. We thought they just sat there and grew bigger forever. But some very clever new physics ideas that have come out just in the last decade or so suggests that's not true. It turns out that even black holes are not perfectly stable. They leak. This is a bit of advanced quantum mechanics, but I can give you the flavor of it. In the empty space, right near the edge of a black hole, the vacuum is alive. Tiny particles are popping into existence and disappearing again. It's a quantum jitter. Occasionally one of these particles falls into the hole and its partner is. To an observer far away, it looks like the black hole is spitting out radiation. We call this Hawking radiation, after the brilliant fellow who figured it out. This means that black holes have a temperature, a very, very low temperature, but not zero. And because they have a temperature, they radiate energy. And because energy is mass, remember Einstein, easy mc2 as they radiate energy. They lose mass. They are evaporating. Now the math here is staggering. The time it takes for a big black hole to evaporate is almost impossible to imagine. It is a 1 followed by nearly 100 zeros. Years. If you wrote that number on a piece of paper, the zeros would stretch across this room. But again, it is not infinity. It is a number. So in the incredibly deep future, long after the stars have gone out, long after the galaxies have dissolved, the black holes will be the only things left. They will be the heaters of the universe. But they too are running on a timer. One by one they will shrink. And as they get smaller, they get hotter and faster. And finally pop. They explode and vanish. And then we reach the dark era. This is where the story comes back to our coffee cup. Remember the lukewarm coffee? It reached room temperature. It couldn't do anything else. It had no potential, no gradients. In this distant future, the universe reaches that state. The matter that is left, electrons, neutrinos, photons, is spread out so thin that it might as well not be there. The expansion of the universe has stretched everything out. The temperature everywhere is virtually zero. Not exactly zero, but uniform. Everything is the same temperature. The water in the mill pool is level. The clock has unwound completely. The entropy has reached its maximum. This is the big freeze. And this is where the implications get, as the title of our talk suggested, terrifying. Because what does maximum entropy mean for life? For thought? For anything interesting? Life, whether it is a bacteria, a human being or a supercomputer, is a process. It is a verb, not a noun. You are a process of processing energy.
You take in high quality energy, you use it to repair your cells and think your thoughts, and you excrete low quality heat. You ride the flow. If everything is the same temperature, there is no flow. There is no way to move energy from A to B. This means that in this final state, nothing can happen. No computation can be performed. No memory can be stored. No heart can beat. Time, in a sense, ceases to have meaning. If nothing changes, if snapshot A of the universe looks exactly identical to snapshot B, then time has stopped. It is an eternal frozen now. It is the ultimate silence. Now I can see some long faces in the audience. I understand. We humans, we like stories with happy endings, or at least stories that continue. We like to think of our legacy as eternal. We build statues. We assume that progress goes up and up forever. Physics tells us something different. It tells us that forever is a long time, and the rent always comes due. The universe is a one-shot deal. It has a beginning, a middle, and an end. This realization, the heat death of the universe, was a shock to the scientists of the 19th century when the thermodynamics guys first worked it out. It felt like a betrayal. What is the point? What is the point of composing a symphony or discovering a cure for a disease or falling in love if the final result is just a uniform bath of cold radiation? If the universe eventually forgets everything, it's a valid question. It's the kind of question that makes you stare at the ceiling at 3 in the morning. But I want to offer you a different perspective, a Feynman perspective, if you will allow me, because I don't find this terrifying. I find it clarifying. First of all, let's look at the numbers again. I said this happens in trillions of years. That is a time scale so vast that it makes the age of the Earth look like a fraction of a second. To worry about the heat death of the universe today is like worrying that your great-great-great-great-great-grandchild might stub their toe on a rock that hasn't been formed yet. It's true, but it's not exactly pressing business. But more importantly, think about what it means to be here now. If the universe started in a hot, dense chaos where nothing could exist, and it ends in a cold, dark void where nothing can exist, then there is this magical window in the middle, the Goldilocks zone of time. We are living in the only time where life is possible. We are living in the time of the gradients, the time of the flow. Think of the odds. The atoms in your body were cooked in the hearts of those burning stars we talked about. They were blasted out into space, they clumped together, they formed a planet, and somehow, amazingly, they arranged themselves into a pattern that can sit in a lecture hall and understand the concept of entropy. We are the universe looking at itself. We are the way the cosmos knows it exists, and the fact that it ends, that doesn't make it meaningless. Does a symphony have no meaning because it has a final chord? Of course not. The beauty is in the music itself. The beauty is in the playing. If the symphony went on forever, just droning on, it would be noise. The structure, the beginning, the middle, the end is what gives it shape. The universe is a song, and we are the notes in the middle of the best part. There is another fascinating angle to this. When we study these laws, thermodynamics, quantum mechanics, we are doing something incredible. We are tiny little creatures on a tiny little rock, orbiting a very average star in the suburbs of a galaxy. We are stuck in this specific time. And yet, using just our brains and a few pencils, we can figure out what happened 13 billion years ago. We can predict what will happen 10 by 100 years from now. We can see the machinery of the whole thing. That suggests that the universe is intelligible. It follows rules. It isn't random magic. It's a puzzle, and we can solve it. There is a deep joy in that. The joy of finding things out. When I look at that coffee cup, I don't just see a cooling drink. I see the collision of atoms. I see the statistics of probability. I see the history of the Big Bang and the prophecy of the Big Freeze, all swirling around in the brown liquid. It makes the world look richer. It makes the coffee taste better. And who knows, physics is never finished. We think we know the rules, but nature has a habit of surprising us. Maybe, just maybe, there is something we missed. Maybe in the deep, deep future, when the universe is empty and cold, a quantum fluctuation, one of those little hiccups in the vacuum, starts the whole thing over again. Maybe our universe is just a bubble in a much larger pot of boiling water. Maybe the winding up happens naturally if you wait long enough. There are theories about that. Poincare recurrence, multiverses, brain collisions. We don't know. That's the frontier. That's for the young people in this room to figure out. But even if this is it, even if this is the only run-through, what a ride it is. So don't be terrified of the freeze. The freeze is the price we pay for the fire, and right now the fire is burning bright. We have stars, we have engines, we have questions, we have each other to talk to, we have the useful energy to make things happen. The most important thing is not how it ends. The most important thing is what we do with the energy we have right here, right now. Do we waste it on nonsense, or do we use it to understand, to create, to explore? Nature gives us a certain allowance of order. It hands us a battery and says, here, this is all you get. It's going to run out eventually. Go play. I say we play hard. I say we figure out every rule in the book before the lights go out. So next time you look up at the stars, don't feel small. Don't feel insignificant because they are big and long-lasting and you are small and temporary. Feel proud. You are the thinking part of the arrangement. You are the part of the universe that can appreciate the spectacle. And next time your coffee gets cold, don't be annoyed. Just nod and acknowledge the second law. Say, I see what you're doing there, nature. You're trying to reach equilibrium. And then if you want, go reheat it. Fight the entropy for just a little bit longer. Create a little pocket of order in the chaos. Because that is what we do. That is what life is. Thank you very much for listening. Now go out there and use your free energy wisely. Class dismissed.